Hello, everybody. Welcome to the afternoon session. It's my great pleasure to... Hold on, my phone has died. Okay, it's my great pleasure to introduce Pieter Abbeel. Pieter is a professor of electrical engineering and computer science at UC Berkeley. His research focuses on robotics, machine learning, and control. And his PhD work with Andrew Ng at Stanford is beautifully combined these three areas. They showed how to, a remote control helicopter could autonomously perform some incredible acrobatic stunts, just through apprenticeship learning. Since moving to Berkeley, he's been a leader in applying deep learning methods to problems in reinforcement learning and robotics. One project of his developed a robot that could pick up crumpled items of laundry and fold them neatly. And this got a huge amount of media attention. And he's also been involved with several startups. Gradescope is a company he founded that uses machine learning techniques to help with marking and grading homework assignments, something that a lot of us might find useful. He recently spent a very productive 18 months at OpenAI, but now has a new venture that aims to bring machine learning and reinforcement learning techniques to bring to bear on robotic automation to try and improve the way manufacturing happens throughout the world. So please welcome Pieter.
Thank you, and thanks, Rob, for the very kind introduction. So let's dive right in. This guy will click. Let's see. So what are we watching here? This is the PR1 robot doing a lot of the chores that we wish robots might be doing for us. But there's a catch. And the catch is that this robot is being teleoperated. Eric Berger, one of the students who built this robot, is sitting inside a harness and orchestrating every detail of the motions that this robot is making. So it's more time-consuming to do things this way than to do them with your own hands. But for us, as AI researchers, AI engineers, this is really, really nice, because what it shows is that the mechanical engineering is there. We just need to now provide the artificial intelligence to make this a reality. Now, when I say just the artificial intelligence, I don't mean to say it's going to be very quick or easy necessarily. I think there's a lot of challenges ahead of us, and that's part of what's so exciting about this. And in this talk, I'd like to share with you what I think are some of the important challenges we need to solve to get robots into our homes and possibly beyond. The first big challenge is that I think we'll need much faster, and with that I mean much more data-efficient reinforcement learning. Let's first make sure we're all on the same page. Not everybody here works in reinforcement learning. What's reinforcement learning? You have an agent. The agent gets to see the state of the environment, or maybe just a sensory observation of the environment. Based on that, takes an action. The environment changes state. There might be a reward associated with that, and this process repeats over and over. The goal for the agent is to maximize reward. For example, if the agent was controlling a self-driving car, maybe there was a positive reward for reaching the destination, a negative reward for not being at the destination yet, and very negative for any bad outcomes like an accident. Reinforcement learning is actually quite different from supervised learning. For example, as the agent takes actions, there is no supervision as to whether these actions were right or wrong. It's only implicitly through the reward that you achieve in maybe a final state you get to that you understand whether the combination of actions that you took was good or bad. Assigning back credit to each of those actions, the credit assignment problem, is a really hard problem, and that's where you get your signal from in reinforcement learning. Another challenge is, because of the feedback loop, things could destabilize. You could end up with your system destroying itself while it's learning. And then there's the exploration challenge, which is doing things you've never done before, because it's the only way to improve yourself based on what you're able to do before. Despite these challenges, over the last few years especially, there's been a lot of progress in reinforcement learning. In fact, reinforcement learning has enabled agents that learn to play Atari games from their own trial and error, going all the way from raw pixel values to joystick actions. It's enabled learning to play classical board games. It's enabled to play some of the current state-of-the-art video games like Dota 1v1. And it's enabled to learn to control continuous systems like this simulated robot here. And what you see here is a robot where you see the learning in action. When it starts out, the neural net is initialized randomly, but then over time, it gets better and better and better at solving the task. What does that mean here? Solving the task means optimizing reward. The reward is higher the further this robot goes to the right, and lower the higher the impact with the ground. And just from those simple specifications, It's able to invent something like locomotion from scratch. We've seen success on real robots. This robot is trying to stack the Lego block onto the corner spot. And as she learns to do this, starting with random initialization, figures out over time how to solve this task. You can also have reinforcement learning take on control problems that are far less intuitive to humans. For example, this is the Super Bowl robot, a robot built by NASA meant for planetary exploration. And what you see here is a robot. The robot is controlling the length of the cables. By pulling the cables or extending them, the center of mass will shift and the robot rolls over. So clearly, some mastery has been achieved in a wide range of environments. In fact, often superhuman level mastery. But how good is the learning itself? For example, DQN took about 40 days if you were to run it real time, whereas humans can learn the same thing in about 2 hours. In Josh Tenenbaum's lab, they did a more careful study on this, and what they found is that humans, after 15 minutes, tend to outperform DDQN after it's trained for 115 hours. So this is a very big gap in learning efficiency. So how are we going to bridge this gap? As a starting observation, let's look at the current state-of-the-art algorithms. TRPO, DQN, A3C, DDPG, PPO, Rainbow, and so forth. Those are fully general reinforcement learning algorithms. That means for any environment that you can mathematically define, these algorithms will be applicable. Now, in practice, the environments you see in the real world are only a tiny, tiny subset of all environments you can define mathematically. For example, what you see in the real world will all satisfy our universe's physics. That's just one of many, many ways you could define dynamics. Mathematically, so many other options available. So the question is, can we develop fast reinforcement learning algorithms that take advantage of this? For that, let's revisit the agent architecture. So we have an agent interacting with the environment. Underneath, typically, we have a reinforcement learning algorithm and a policy or a queue function. It's equally applicable to queue functions as to policies. I'm just being concrete here and putting a policy down. So the reinforcement learning algorithm, when faced with an environment A, will train the policy to become good, that is, master what needs to be done in environment A. When faced with environment B, the reinforcement learning algorithm can be reused to train a new policy for environment B, and so forth. In traditional reinforcement learning research, human experts develop the reinforcement learning algorithm and then rely on the reinforcement learning algorithm to train the policy. But they're both inside the agent. And after many years of human development of algorithms, it's actually still the case that none of these algorithms are as good as human learners. Maybe I should take a step back and let the system learn more. That is, why not let the system learn the entire agent, both the algorithm and the policy, rather than only letting it learn the policy? So when I'll use the term meta-learning in this presentation, what I'll refer to is an approach where the learning algorithm itself is being learned. That's what the meta refers to. So meta-reinforcement learning means learning to reinforcement learn. What can we hope for? From the intuition we've gotten so far, it's the case that if we want something to learn faster, it probably needs to understand our world better. Have seen many situations in our world such that when it sees a new situation, it can pick up on it more quickly. So maybe this meta-learner would be faced with many environments, A, B, and so forth, somehow do something with them, and then output a faster reinforcement learning agent that when faced with a new environment, F, or G, or H, would quickly adapt to that new environment and do the right thing. Now, how to formalize this? This is what we want, but we still need to somehow have a way to do it. Here's one way to formalize this. What we're after is an agent parameterized by a vector theta. Theta is some numbers, let's say. It could be parameters in a neural net. It could be an encoding of what some program looks like, anything really. We try to find a theta that is such that it maximizes this objective, which is, on expectation, if you sample an environment and then get to act capital K times in that environment, this agent will optimize reward over those capital K episodes it gets. Pictorially, what it looks like if capital K were equal to 2, this agent would be dropped in an environment, gets to act for 2 episodes, then gets dropped in a new environment, gets to act for 2 episodes again, and this repeats over and over and over. And what we want is not an agent that masters one of these environments, but an agent that is generally applicable to any new environment you're going to drop it into and quickly learn how to collect rewards in that new environment. So at training time, what that means is we'll sample a bunch of environments, the training environments, and optimize this objective over the training environments. We still need to decide how we're going to represent this agent. It can be a lot of things, and you should probably make some choices of your own in your future work and have a better choice than we've made so far. But let's look at what we've done. So what we did is we put a recurrent neural net inside that agent. Why? A recurrent neural net is a generic computation architecture. It has storage, has compute. And we want to be very open-ended, allow it to learn anything that might be useful to be an RL agent. If we look a little more deeply, what this means is that the weights of this recurrent neural net will correspond to a combination of the reinforcement learning algorithm the agent is using, as well as a prior the agent has from interacting with past environments. And then the activations, as it's acting in a new environment, will correspond to what it's fine-tuned in that new environment in terms of policy. How do we find this data? If we look at this objective, this is actually still a reinforcement learning objective. So we can actually train to find the RL agent data by running reinforcement learning on this meta objective. So we'll bootstrap from existing slow reinforcement learning algorithms to learn a hopefully faster reinforcement learning agent. To evaluate this, one place to start could be multi-arm bandits. In multi-arm bandits, you are faced with a bunch of bandits. Each bandit you can choose at any given time, and each bandit will have a probability of payoff. And you don't know the probabilities ahead of time. So your job is to figure out which ones have higher probabilities of payoff, and then pull those more often than the ones that have low probability of payoff. This is a classical exploration exploitation type of problem in its simplest form. In this setting, researchers have come up with provably optimal algorithms, provably asymptotically optimal algorithms to solve this problem. So we're going to compare with those. This will give us a metric of how good an agent are we able to learn compared to the optimal ones for this kind of environment. It turns out that RL squared is competitive with the asymptotically optimal algorithm Gittes indices. This is pretty interesting because that means that we can do as well as the asymptotically optimal by just learning the algorithm rather than designing it. Here's another environment. Here the task distribution is will always be controlling a cheetah robot, but it'll vary what the desired speed and direction is. So what we hope for here is that as the result of meta training, an agent that when dropped in this new environment learns to control this cheetah robot almost instantly at the desired speed. And indeed, this is what's happening here. What you're seeing here is for every task, now run at speed 0.5 is the task, then now the task is run at speed 1.0. What we're watching is the very first rollout of this agent in this environment under this task specification. At training time, it's seen other task specifications that I have to control the cheetah for, but then at test time, it gets new ones and is able to adapt instantly. We can do the same thing for ant robot. What you see here is task is run forward. We see the first episode. It's the first episode now for the task of running backward. Within the first episode, it masters the task. Again, first episode masters the task of running at speed 0, now 0.5. Of course, this is a somewhat narrow task distribution, so you might expect this is going to work reasonably well because it can focus on a very narrow task distribution. Here's something wider that also involves vision. Here our agent has to navigate a maze it's never been in before. It just gets monocular images. It's supposed to navigate this maze to go to a destination. It doesn't know where that destination is. We can see the destination because we have a map. That's just for our purposes, to watch the agent act, but the agent doesn't have that map. So what we're hoping for is that if this agent is really well trained for this, you can drop this agent into a new maze, and in that new maze, it'll instantly explore the maze in a very effective way and then go to the target. And then if it gets dropped in that maze again, it'll quickly go to the target because it remembers what it's seen before. This is random exploration, doesn't do much good. Here is the fast RL agent that has been trained on many, many mazes in the past, now gets dropped into a new maze, again, does not have access to this map. Just gets the monocular images, and somehow it has figured out a strategy to adapt to this situation, and when it gets dropped in the same environment again, it instantly goes to the goal. It doesn't work all the time in that these are the meta-learning curves. About 2/3 of the time, meta-learning succeeds. About 1/3 of the time, it doesn't succeed. Why might meta-learning not succeed? Actually, two reasons it might not succeed. One reason is overfitting. You overfit to the maze you're currently faced with, and you learn to solve that one instead of learning to generically solve mazes. That's always the case in learning. You need to avoid overfitting. You can actually also underfit here. It might be that you just don't get enough signal to even get any rewards and be able to learn this skill. One way to propagate more signal is to maybe put a slightly different structure underneath. So one thing we looked at is to put underneath, instead of a recurrent neural net, which might have a little trouble over long horizon to propagate signal, underneath put a wavenet-like architecture. But of course, then we lose some details, and we add on to that attention so we can also look at the details from the past. This architecture called Snail can then be swapped in for the RNN, and you can run the exact same kind of process as we did before. Turns out it actually gets more signal, is able to do a little better on the bandits problem than RL squared, and it's also able to solve bigger mazes. Here's an example of such a big maze. We see the agent, the trained agent here, starting off, took a bad turn unfortunately, but it doesn't know that because it doesn't have the map. It just gets the first-person imagery. It very efficiently explores this maze, doesn't waste any time doing things that are unnecessary. Realize that's the end of the maze there is nothing more to be done on that side. Starts working its way back. And what we see here is that it's a very efficient explorer of mazes it's never seen before. And again, this is all from first-person vision. One more unlucky turn. But then the final thing it explores is actually gets to the destination. And again, this maze is not seen at training time. We can even put more structure underneath if we'd like. In mammal, our starting observation is computer vision practice. So what do people often do in computer vision? There's this beautiful data set called ImageNet. You train on ImageNet, have your neural net trained on ImageNet, and then you have an actual task you want to solve, and you fine-tune on the actual task. It actually works quite well. So some questions from there are, how to generalize this to behavioral learning rather than image recognition, and instead of just training on something and then hoping for the best that fine-tuning will do the job, can we end-to-end learn to be ready for fine-tuning when the real new task arrives? So the key idea we're pursuing is, can we do end-to-end learning of a parameter vector theta that is a good initialization for fine-tuning for many new tasks? So at test time, what we're going to do is fine-tuning. What does that mean? We have a pre-trained parameter vector theta. We get a new task. We evaluate performance on a new task, compute a gradient, do an update, and get a fine-tuned parameter vector, theta prime. Now, the hope is that this parameter vector theta prime is a good one for this new task. If that's the case, we were successful. So how do we train for this? Turns out we can train this end-to-end. At training time, we have a distribution over tasks, and we try to find a parameter vector theta that no matter what task you sample, and from that task you sample a few training examples, a few validation examples, you take a gradient based on the training examples, and after that gradient, that fine-tuning step, it should do well on the validation examples. If that's true, that parameter vector theta is really ready to be fine-tuned from. Okay, so pictorially what this looks like is that there are many, many tasks. They all live in some parameter vector space theta, the solutions to those tasks. And what we want is to find this parameter vector theta that is somewhere between the solutions to many tasks and ready with one gradient step to jump onto a solution to a new task. Turns out, I'm not going to show the same kind of videos again, but it gets competitive performance on the bandits problem, cheetah, and that we already watched. It's actually some interesting theory too. Mammal has recently been shown by Chelsea Finn and Sergey Levin to be fully general. What's meant with that is that even though it seems like it's a little constrained because it relies on fine-tuning as the underlying learning rule, whereas RL squared and Snail can rely on anything a recurrent neural net or a wavenet can represent, this relies on a gradient step, but it's actually possible to prove that it doesn't lose any generality by relying on this gradient step. Really cool result. Meta-learning is not only done for reinforcement learning, it's actually been done quite actively for optimization, and I'll share the slides after the talk so you can go read a lot of these references if you'd like. It's done quite a bit for classification. Interesting fact is that while mammal and snail were not designed for classification, they also work for classification, and on release of each of the papers, they were actually state-of-the-art on also meta-learning for classification, not just on reinforcement learning. Exact same approach. You can apply this to generative models, and actually there's also quite a bit of work in reinforcement learning, and the later references we'll touch upon in the remainder of this talk. So there's not just faster reinforcement learning that I think we'll need to solve the AI robotics puzzle. We also need to learn to reason over longer horizons than canonical RL algorithms will do for us. So why would we want hierarchy? Well, imagine you have a home robot. And maybe you say, well, it only needs to do 10 tasks today, maybe some dishes, some cleaning, some cooking, 10 total, 10 decisions to be made. But the truth is, those 10 decisions need to be incarnated in something below it. Maybe moving somewhere, grabbing something, placing it somewhere, and repeat that a few times. So really then it's 1,000 time steps the robot has in its day. But actually going somewhere requires many footsteps. And so maybe the robot really has 100,000 time steps in its day. And footsteps require commands to be sent to motors, and that might be needed at 100 hertz. So actually really we have about 10 million time steps in the robot's day. That's a very long horizon compared to what we've seen in pretty much any reinforcement learning results so far. To go for 10 million time steps, learn something over that horizon. Very big open challenge. Of course, people have been making progress on this challenge, but I think it's fair to say that this is far from solved. There's a lot of opportunity to make progress here. Here are some examples of some older and recent progress on this problem. And they all center around defining temporal abstractions or even learning temporal abstraction models to make this more tractable. The angle I want to highlight here is that actually we can formulate this as a meta-learning problem. The meta-learning problem is as follows. The agent has to solve for a distribution of related long horizon tasks with the goal of learning new tasks in the distribution quickly. If that's our objective, then hierarchy should kind of fall out. Now, it might be a lot to hope for that it'll just fall out. We'll give it a little more structure. So we'll have a master policy which acts infrequently, theta, and the sub-policies phi 1, phi 2, phi 3, and so forth, which get to act at full control rate. The master policy decides at any given time which of the sub-policies is active. And the meta-learning objective here is, can we somehow find sub-policies, phi 1, phi 2, phi 3, such that if the master policy has access to those and gets dropped in a new environment it's never seen before, relying on those sub-policies is a very effective way to master those new environments. So, this is what meta-learning looked like before. Now we want this hierarchical structure. We changed it a little bit. We want this template to be incorporated. So what we're training for is phi. Phi is the parameterization of the sub-policies. We want to find sub-policies such that if we randomly initialize the master policy with some theta 0, and then this master policy gets to act in a new randomly sampled environment, M, for capital K episodes, it should collect high reward. Now the master policy is not just a policy, it will actually be a reinforcement learning agent that will improve over time what it's doing. So you want these sub-policies to be such that an agent acting on top of it benefits from them and can learn quickly. The agent on top of it, theta, you might maybe train in the future with some meta-learning like we've seen with RL squared, snail, mammal, and so forth. In the experiments I'm going to show to you, the RL agent is just running PPO. Here's an example you could test this on. Moving bandits. It's a bandit problem, but the bandits are not just available to you to choose from. You have to walk to them, run to them, to actually be able to pull them. So what you'd hope for in this scenario is that a sub-policy would correspond to moving to the green object, another sub-policy would correspond to moving to the blue object. And indeed, that's actually what emerges. We don't have to hard code this into the system. We just let it discover two sub-policies that make it effective to explore this environment when you encounter a new incarnation of this environment, and those are the sub-policies that are learned. Here's another example. Let's say your ant needs to navigate a maze. Very low-level control needs to happen, as well as high-level decision-making about where to go. You'd hope that at the low level you invent locomotion gates, and at the higher level you invent something about how to navigate and explore mazes. In fact, that's indeed what happens. And the beauty here is that we don't explicitly train for any of these gates. These are the gates that emerge as gates that are helpful to help the high-level policy to quickly learn to collect reward in a new maze. Reinforcement learning is great, but there's actually other things we want from our robots. We want to be able to task them, tell them what to do. And one way to tell them what to do is to maybe teach them by giving examples. There's been a lot of success with imitation learning in robotics. In fact, there's been success in helicopter flight, legged locomotion, predicting where taxis might be going, learning to tie knots, and placing dishes into a dish rack, and many, many more. Here's the typical paradigm. You collect many demonstrations, then you train something from those demonstrations to match, in some sense, what's happening in those demonstrations. And then after that, you deploy the learned policy, and hopefully it does well. And actually, often it does. You want to assemble a chair, you get demonstrations for assembling a chair, you learn a policy, you deploy. You want to assemble a table, same thing, and so forth. Now, the not so great thing about this is that anytime there's a new task, you start from scratch, and you need a lot of new demonstrations. Humans are not like that. For a human, you can give one demonstration of a task and they get it. Maybe not when they're a 0-year-old, But once they're a little older and they've seen the world and experienced what tasks can be like, then one demonstration is enough because they can tie it into what they've seen in the past. So we'd like the same thing here. Once you've seen many demonstrations, can you extract the essence of what a demonstration is, so one demonstration is enough to learn something new? So what we'd want here is a one-shot imitator to be learned, something that can take in one demonstration and that's enough to do the right thing. Based on having seen many things in the past, of course, but then it's going to learn something new in the future. For example, a demonstration of task F or G and learn it from just one demonstration. How do we train something like this? Well, here's one way to do it. The red box here is the one-shot imitator neural net. So that's what we're training. The way we're training it is by saying, we'll have 2 demos of each task in our meta training distribution. Demo 1 of task I, demo 2 of task I. The one-shot imitator gets to look at the entire demo 1, parse it in whatever way it wants, maybe run a recurrent neural net over it to make sense of it. Then it gets to see 1 frame from demo 2 of the same task. It also knows what the person did in that situation and has to predict the corresponding motor torque. So this is a supervised learning problem to train a one-shot imitator. If you train it with enough tasks, you'd hope that it would generically learn the notion of one-shot imitation. We tested this on block stacking. It's actually a hard task because we're doing low-level control here over a very long horizon. If you stack 7 blocks, that's many, many low-level control steps you need to go through to do this. The task distribution here is random set of blocks in front of you in random locations, one demonstration of how they should be stacked, maybe A onto B, C onto D, J onto I, something like that. From that one demonstration, you need to learn what to do with the same set of blocks in a new initial configuration. What we're watching here is on the left, the demonstration, and on the right, the one-shot imitator's policy. And we see it's actually doing the right thing. It's picking up the right blocks, placing them onto the right target blocks. The highlights at the bottom that you see, those are the attention models. So the bottom right shows you that right now, the one-shot imitator policy is paying attention to blocks F and G. All 4 heads of attention are in F and G. On the left, the horizontal axis is time. So you can see what times the one-shot imitator is paying attention to in the demonstration. It's a soft attention, so effectively it looks at everything, but we highlight where it pays the most attention to. And so we see that just from one demonstration, it's able to learn to stack blocks. This here was done in state space. So we represented state of the blocks. We've also looked at this, doing this from raw pixels. So here we did it with MAML, so a different way of training. Again, MAML is where you have a pre-trained parameter vector theta. That's a neural net that goes, in this case, from pixels to actions. And you get a few examples for a new task. In this case, you behaviorally clone train on those few examples, and it should then be ready, be fine-tuned to solve that task itself. We actually have different objects at meta training time than at meta testing time. So when we show a demonstration to the robot, that demonstration is using objects it's never seen before. On the left is a demonstration, placing the object into the white bowl. Okay? It sees that demonstration once, and then it learns to do the right thing. What we're seeing here is the robot's view. The robot is taking in raw pixel values and deciding what to do with the end effector, all the way raw pixels to motor commands. If now the demonstrator demonstrates something else, placing it on the yellow placemat, it learns to do that, just from one demonstration. Okay, so we've covered some reinforcement learning, some imitation learning. It's another thing that's going to be really important if we want robots in the real world, which is lifelong learning. Again, many challenges there. What is lifelong learning? Well, let's first take a look at what we do right now in machine learning. Typically, step 1 is you run machine learning. Step 2, you deploy. Very canonical way to put machine learning into practice. So all the learning happens ahead of time, before the deployment. But in the real world, often things are non-stationary. And what you learned on past data might not work anymore later. So really, you'd want something that can handle those ever-changing situations. You want something that still learns during deployment. That spirit is the lifelong learning spirit. There's actually been quite a bit of work on this and how to get systems to continue to learn. And the angle I want to look at here is the continuous adaptation of behavior angle. So where you look at, can we train an agent to be good at dealing with non-stationary environments? So when we did meta RL so far, we trained an agent to be good at adapting to a new environment. But now we want an agent to be good to adapt to a changing environment, a constantly changing environment. So again, we can phrase this in a meta-learning way. What we're trying to find is an agent parameterized by a vector theta that is such that if it faces a sequence of tasks, that it is good at solving that sequence of tasks. And those tasks might have some dynamic pattern to them, such that at meta-training time, you can start understanding what typically happens as things evolve and anticipate some things that will happen later. What are some example sources of non-stationarity that we can infuse? Obviously, in the real world, there's a lot of non-stationarity, but it's difficult to do machine learning research in the real world. So what can we do in simulation, maybe? One source could be changing the dynamics, something we looked at in the paper, but I'm not highlighting on these slides here. Another thing you can look at that makes it a little easier on the designer of the environments is actually competitive environments. So what this means is that you're in an environment where there's other agents. These other agents are trying to beat you to it. And these other agents are running reinforcement learning. So they're constantly changing, trying to become better at beating you. And so now the only way you can do well in this kind of environment is by yourself continuing to adapt, and actually hopefully adapt more quickly than the other agents so you can beat them to it. It's a very natural way to infuse more and more variation just the longer you run things. We evaluated this in the context of robo-sumo wrestling. In robo-sumo wrestling, you're supposed to either push the opponent off the tatami or you're supposed to flip them over onto their back. If you do that, you win. If the other robot does it to you, you lose. Okay, so let's watch some robo-sumo. What should we pay attention to here? Initially, the green one, the six-legged bug robot, is winning most of the time. It's actually been trained to be a little better than the other one. But as they play each other, the green one is just running standard reinforcement learning, and the red one, the four-legged one, is running what has been trained through meta-learning to be a fast adapter in non-stationary environments. And we see that that allows the red agent, the ant robot, to actually start dominating over time. And so we see here the benefit of being ready to adapt quickly in these kind of adversarial environments. In fact, we can highlight that even more by looking at a population study. We let a bunch of robot spiders, bugs, and ants loose in this environment. When you get let loose, what it means is that you get randomly drawn against another opponent. You play 100 times. During those 100 times, you're both probably adapting your strategy to be better in the next round against that same opponent. After 100 times, we evaluate who won the most. That one survives, the other one's gone, and we repeat. And what we see here is that the meta-learners, the ones who have been pre-trained to be good at adapting, dominate this kind of process. One other thing that I think will be really important to become better at if we want to deploy robots in the real world is to leverage simulation. Simulation is really helpful. It's less expensive, it's faster, more scalable, it's less dangerous, it's easier to get labels because they're built into your simulator. But the challenge, of course, is how to get useful signal out of your simulator for things you want to later do in the real world. Well, one approach is to just build really realistic simulators. You do that, you're all set. And a lot of great efforts have happened in that direction. The slight flip side of this is that you need to build a really good simulator, which is not easy to do. And that simulator might be somewhat computationally expensive. Because let's say you want to simulate the entire world or something, that's going to be one expensive computation to run. Something more intermediary would be to say, I'm going to have simulation that is not necessarily perfectly reflecting the real world, but I'm also having some real world data. I'm going to find a way to line them up, implicitly or explicitly, maybe through domain confusion or domain adaptation type techniques. And that might allow you to learn more quickly from a smaller amount of real world data thanks to the simulator data that is associated with it. And that's actually been quite successful. The direction I want to highlight, and which I think is kind of surprising how well this has been working, something that kind of the success was really surfacing over the past year only, is domain randomization. The idea here is that if the model sees enough simulated variation, even if none of it is realistic, like you see here on the left, none of that looks like a real image of a robot in front of a table with blocks. They're all clearly rendered images. Even if none of that is realistic, maybe there's enough variation in lighting, texture, viewpoint, occluders. What you learn in that simulator could directly carry over to the real world. I started looking at this after seeing some results from Ferzheh Sadeghi and Sergey Levin, who looked at this in the context of training a quadcopter purely in simulation to then be able to navigate reliably in hallways in the real world. It was really surprising to me that this worked, so we started looking at this then in the context of robotic manipulation. Can we train purely in simulation and train a system that just from simulation can estimate reliably the pose of a block of interest and then pick it up? And in fact, this was possible. So the neural net controlling this robot got no real-world training data, only simulated rendered images that are not that realistic, was able to, in the real world, identify the block that it was supposed to identify. Now it's supposed to find the hexagonal block, and it actually finds it, never having used a training image from the real world. What's maybe even more surprising is that we didn't even need any pre-training. So we compared this with if you pre-train on ImageNet and then train in simulation versus you just train in simulation, and after about 8,000 simulated examples, performance is a tie between the two ways of doing it. Now, simulation can hopefully get us far, but it's still the case that likely we'll need real-world data. And so I think one important thing we need to continue to face is that we want to extract as much possible signal from our real-world data. So maybe some of you, I guess the way NIPS is growing, only half of you were last year at NIPS and might have seen Jan LeCun's keynote. And this keynote featured a cake. Okay? So this cake has been reused a few times since. And what is this cake representing? So this cake is a chocolate cake with a cherry on top. We all know the cherry is a special part. Now, Jan LeCun said the cherry is reinforcement learning, and there was a whole explanation about this, in that the cherry is reinforcement learning. What does that mean? It's this tiny little thing on top. It's really important, it's really cool, you really want it, but it doesn't give you a whole lot of signal. So maybe you need to do some other learning too. Frosting, higher volume than the cherry, corresponds to supervised learning. You get more bits per example in supervised learning than you do get in reinforcement learning. And then, of course, there is the big mass, the cake itself, and that's representing unsupervised learning. Anytime you see a video, the next frame you could try to predict, and that's a lot of bits of information you're trying to predict. Now, of course, in reinforcement learning, it's not the case that people only look at the cherry. In fact, there's a lot of work where people look at the entire cake and train reinforcement learning agents to take signal from both the reward and auxiliary signals. For example, this enabled solving complicated mazes like the DeepMind lab mazes. So what happens here underneath is that you set up a neural net that has multiple heads. One of the heads is still the policy output or the Q function output, but then other heads correspond to maybe next frame prediction, things like that, auxiliary losses. And this allows you to learn good representations at the core of your neural net that can be used for both the auxiliary loss prediction and for the policy output. I think it's very promising. We need to continue pushing this very hard. What I want to highlight here, though, is something a little different. Is that we don't need to restrict ourselves to this kind of cake. How about this kind of cake? So this cake has a lot of cherries. And I'd prefer to eat a cake with a lot of cherries, because I like reinforcement learning. So the question now is, it's easy to put up a picture of a cake with more cherries and even make one, maybe. I don't know, I've never made one, but I think it's not too hard. The question is, can we actually tie some reinforcement learning ideas into it rather than just show a picture? One way to get there is an idea called hindsight experience replay. It's actually a paper at the main conference this year. It builds on a lot of prior work in similar directions of trying to infuse more signal into your reinforcement learning agent, but signal that's more directly related to reward rather than just auxiliary losses. And our work here builds very directly on the universal value functions from Tom Schall and collaborators presented at ICML 2015. So what is this hindsight experience replay, or this cake with many, many cherries? The main idea is that we want to get reward signal from anything the agent does, not just from success. But reinforcement learning tends to give reward when there's success or bad, failure only, not from other things. So what we're going to do is we're going to somehow, after the fact, assume that whatever the agent did is success. As we were discussing this at OpenAI, the way Wojciech liked to put it was, your agent is supposed to get ice cream for you, but it ends up in the pizza place. It brings you pizza. You could say 0 reward, nothing to be learned. That's classical RL with 1 cherry. Or you could put all the cherries on the cake and say, hey, this agent should have learned now about how to get pizza for you. That's what we're going to try to do. What you need is a different representation. You can't use a classical queue function with just state and action. You need a goal explicitly in your queue function. Because once you have that, you can learn against multiple goals at the same time, and you can, in hindsight, infuse goals that you achieved even though they were not really your goal when you were acting. So, we still have a replay buffer, collecting experience. In that replay buffer, standard queue learning with experience replay would replay that experience by doing stochastic gradient descent on this loss over here. Often the reward will be 0, there will be a 0 signal in it. What we can do now is whatever happened, we call our goal in hindsight, we replay off policy clearly, but queue learning works well off policy, no problem there, so we replay off policy, infuse a new reward, a new goal associated with that reward, and get signal from everything the agent has done. Once we do that, we can get some pretty complicated things to work with pure model-free reinforcement learning, no auxiliary losses except for this hindsight experience replay idea. So on the left here, you see what happens if you use hindsight experience replay. After 20 epochs, it has a 7% success rate, 30 epochs, 30% success rate. And on the right, you see the exact same algorithm. Exact same thing is happening on the right, except when it replays experience, it does not hindsight swap in the more signal-full reward or goals. Same thing is true for a task like sliding. By after the fact, infusing goals and rewards that associate with what you achieved rather than what you were trying to achieve, you get a lot more signal and can learn pretty complicated skills in a reasonably small amount of time. Comparing the learning curves, we see that indeed, also over many runs, this way of learning is quite a bit faster than if you don't do the hindsight experience replay. One thing to keep in mind here is that you need an off-policy method for this idea to apply very directly because you're infusing off-policy information in your replay. So one thing I hope I've done in the 40 minutes so far is to tell you a little bit about what is so exciting about working in AI for robotics and how there are many, many challenges ahead of ourselves, and it's a good time to be working in this space. There's many more challenges than the ones I've touched upon, so it's an even more exciting time than I alluded to. But now for the last couple of minutes, what I want to do is take a little step back on what I discussed and see where, at a higher level, maybe things are headed. So one thing you might have noticed that a recurring theme in the talk was meta-learning. Meta-learning this, meta-learning that was often the solution to the challenge. Not the solution, is the wrong way to put it, and some progress on these challenges. The beauty of meta-learning is that it enables discovering algorithms that are powered by data and experience rather than just human ingenuity. And I'm inclined to think that the more data you can put into your algorithms, the more experience you can put into your algorithms, at some point, you're going to be putting in more experience than any single human has ever experienced themselves. And so in principle, your algorithm should be able to be better than what any human can design, or maybe all humans combined can design. And in fact, of course, this will require more compute, but the truth is that as machine learning is becoming more and more monetarily valuable, we also see more and more advances in compute dedicated to machine learning. Companies like NVIDIA, Intel, Google, GraphCore, Cerebras, and so forth are going to give us more and more compute in the next few years, which I think will empower even more so the meta-learning approaches to solving these kinds of problems. Thank you.
Okay, what a wonderful talk. All right, so any questions? Please come up to the microphones. Okay, well, while people are doing that, maybe I'll just ask one initially. So, one high-level theme, of course, of NIPS, I guess, is dealing with uncertainty. And of course, there's lots of uncertainty in the world. And I mean, how's that reflected in some of the things you're talking about?
Okay, so Rob's question was about how to deal with uncertainty in these kind of settings. I did not include it in this talk per se, but I think that also ties very closely into things like safe learning and combining planning and learning. So whenever there is uncertainty, ideally your neural net would be aware of this kind of uncertainty and would account for that in its planning, learning, to maybe make safer decisions that you could make otherwise. So one angle of safety, might even have a slide somewhere here, not sure if I can find it quickly. One angle of safety is, how do you safely learn? How do you not destroy the system during learning? And that's where I think Bayesian approaches become very valuable. How do you understand the amount of uncertainty you still have, so you can maybe fall back on a safer policy than just what's mean optimal? Another angle for safety that I think is very important to investigate is how to continue learning once you already have 99.9999% success rate. Because that might not be enough to be better than a human driver, let's say. And so how do you keep getting signal once that starts happening? Very important problem. Another really important problem there is, once you build really good AI contraptions, how do you make sure they align their value system with our value system? Because at some point, they might be smarter than us, and it might be important that, they actually care about what we care about, and how to infuse that kind of caring, our value system, is another big safety challenge. So yeah, a lot of challenges there, very important to think about.
Hi, Peter. Thanks for an awesome talk. I just had a question regarding lifelong learning. So I'd like to know some of your views on how one specifies change in this setup for better evaluation of algorithms.
Yeah, so that I would say both in meta-learning for RL and in lifelong learning, I would say one of the biggest, maybe the biggest challenge is to set up good evaluation environments for these approaches. It's clear you want it in the real world. It's also not clear how to do research in the real world that's effective and fast. And how to set up good evaluation environments is really, really hard. So that's where our thinking has been leaning in the direction of competitive environments a little bit, because that lets changing environments emerge. But that's just one direction. And sumo wrestling is obviously still quite a constrained environment and not as rich as you would want it to be. But maybe if you build richer environments, rely on something like Minecraft, where there is more opportunity to invent interesting strategies, maybe even more interesting non-stationary effects will emerge. But I'd say that's a very open problem to even define the right way to evaluate these approaches.
Thank you. May I add something?
Sure, yeah.
Yeah, so I do see that a multi-agent setup is one really good way to specify change. And I guess there are ways of understanding complexity of these systems from some mathematical perspective as well, which could help with evaluating algorithms and tallying them against how complex a system or emergent system is. Yeah. I don't know if I made any sense there.
Well, I'm not 100% sure there was a question.
Yeah, it was just a comment.
Okay,
Yeah.
Okay, thank you.
Thank you.
Oh, hi, Peter. One question is for theoretician. If we want to contribute to the study of meta-learning, what are the key problems we should look into?
To machine learning in general, or specific?
Meta-learning.
Oh, meta-learning. So I would say each of the sub-disciplines of meta-learning has challenges. That is, meta-learning for optimization, for supervised learning, for unsupervised learning, and for reinforcement learning. Then within those, I would say one of the big challenges is to even understand what environments you should train in. So that's a big challenge. What are the data sets or the environments to work with? Another big challenge is designing new architectures. So the architectures you see here are just a few examples of architectures. But what we've seen in disciplines like computer vision is that new architectures emerge regularly that outperform past architectures. And it's quite likely the same will be true for meta-learning, that the architectures I've shown to you here are by no means the ones people will be using 2 years from now, maybe not even a year or a half year from now. There's a lot of room for designing new architectures, especially, I think, architectures that have more explicit memory aspects to them. We explicitly store information, retrieve information, do things like that. Then algorithmically, some of the challenges tie into overfitting, which you need to be careful about because you have a distribution over a task. You don't want to fit to the one task you're currently training on too much. And then underfitting, which is when you have a distribution over tasks, how do you make sure you extract the essence of that distribution over tasks rather than getting no signal at all about the essence? And so there's a lot of challenges in that regard. One place you might also want to look is Rocky Dwan, third person on the picture board here, is posting his thesis next week. And the last chapter of the thesis has a bunch of suggestions on interesting future work directions within meta-learning that might also be a good resource to look at.
Thank you.
Okay, so unfortunately we're going to have to stop questions here and move on to the rest of the session. Let's thank Pieter again.
Thank you.
There's just going to be a short break to allow people to move to the other hall if they want to attend the other session.